So let's start by repeating the solution for nitrogen like before. As we solved before, if you were to solve for atomic mass, you'd plug in each of your percents with their masses and solve to get out to 14.007. Like before, the average atomic mass was the unknown calculated. However, we can use the same formula to calculate the two percent abundances. So you might protest that we have two unknowns, but only one equation. And you would be right, except there is a trick. And the chem team loves tricks. Think about the sum of the percent abundance of the two isotopes. The sum of the percent abundances. That's right, they add up to 100%. They add up to 100%, but since when we calculate percents, we put them in decimals, they add up to 1. Okay. 0.99 plus 0.01, or 99% plus 1%, would add up to 1. So the trick is to express both abundances with only one unknown. Express both abundances with only one unknown. So for nitrogen, if I have the two isotopes, N14 and N15, and the average atomic weight, what is the percent abundance of each? Well, we'll plug them in. If N14, you put its mass in the 14 spot. We don't know its percent, so there's an X there. For N15, you put its mass in the mass spot. We don't know its percent, so we put 1 minus X. And then the atomic weight is 14.007. So instead of placing X and Y as two variables, the two variables add up to 100. So we have X as the percent of 14. We know it will be the percent of 14 because we've written it with 14. Mass times the percent. Plus 15 times its percent. Well, its percent will just be the rest of the percent, right? The two percents together are going to add up to 100. So you plug in X here and 1 minus X here. If I solve this using basic algebra, distribute 15 and negative 15x, you get 14x plus 15 minus 15x equals 14.007. Continue with the algebra. Subtract 15 from both sides. Combine like terms. And you get x equals 0.993. So x is 0.993, also known as 99.3%. So what does this percent mean? Well, we had the x written in the equation right here. We said 14x, 14 times x, which was the mass 14 times the percent, which we didn't know. We just solved for the percent. We solved for x. So that's the percent of N14. Now to find the percent of N15, well, the two percents together must add up to 100. So we know it should be 0.7%, because the 99.3% plus 0.7% makes 100, right? So we know that the two percents have to add up to 100. So by solving for x, you automatically find the other percent, because they must add up to 100. So we plug in x and 1 minus x. My 1 minus x comes out to 0.007, which is 0.7%. So, for example 2, copper is made up of two isotopes, copper 63 and copper 65. Given copper's atomic weight of 63.546, what is the percent abundance of each? Okay. So once again, I plug things into my equation. The mass 63, the mass 63. I don't know the percent, so I put x. The mass 65, the mass 65. I don't know the percent. I've already used x, so this time I'll use 1 minus x. The two of these added together gets me my average atomic mass, which in this case is 63.546. So you just plug in the variables you're given and then solve for x. When you solve for x, one of these isotopes, the percent should be around 70%. So solve for this and see which one should be around 70%. So to solve for x, we have 63x, right? You multiply these two together. Then we distribute, okay? Plus 65 minus 65x equals 63.546. Okay? So 63x and the negative 65x, you combine like terms. So if I combine like terms, I get a negative 2x plus 65 equals 63.546. Okay. I'm wanting to get x by itself, so I need to subtract 65 from both sides. It's being added on this side, so I need to subtract from both sides. So you get negative 2x equals a negative 1.454. Now I still need x by itself, so I need to divide both sides by a negative 2. This is being multiplied by a negative 2, so to get x by itself, I need to do the exact opposite. Divide by negative 2. And in that case, x equals 0.727. Okay, now this is the decimal form of the percent, which would equal 72.7%. Now to figure out which element has this percent, well, where did you put your x? We said that the x is times 63. So that means my percent for 63 is 72.7. So my percent for 65 must be the other part of the 100%. If this is 72.7, then the other must be 27.3. My 2% must add up to 100. Now for a last note, this only works if there's only 2%. If there's more than 2%, it doesn't work, because then we'd have way too many variables going on. But if it asks for you to solve for percent abundance and there's only 2 isotopes, that's what you do. So Bohr's theory. Bohr's theory is the model in which you have the circles around the element with each of the electrons in their orbital in the electron cloud. Remember, it's called the planetary model. Now Bohr's theory, this planetary model, also brings in these light wavelengths we've been talking about. So when white light is passed through a prism, it is separated into its components of the spectrum, or the rainbow of colors. What then is white light made of? This rainbow is called a continuous spectrum and includes all of the visible wavelengths. When atoms are excited, they emit light, but not as a continuous spectrum. When atoms are excited, they emit light, but not as a continuous spectrum. And what we mean by excited is energy has been added to them. There's several ways to add energies. One of them would be to catch the element on fire, which is what we'll be doing in the flame test lab. The other one is to add electricity. That would also excite the electrons. The light that is emitted when they are excited is emitted in a specific pattern of visible colored lines, which is particular to each element. We call this a line spectra, and it can be used to identify individual elements. So hydrogen always emits this spectra. It will always emit a little purplish line, blue, green, and red at these wavelengths. Those are the only lights it emits. Now, with your human eyes, when you look at it, you will not see all 4 of these colors. You need a prism to actually break it apart. we see combined colors. Just like when you look at the ceiling light, we see white light. It's not emitting a white light, there's no color white. It's emitting all of the colors and we see white. When you see a yellow light bulb, that one is not emitting yellow. It's emitting everything else, so we see yellow. Okay, so our eyes combine these colors together. So in order to see the actual line spectrum for each element, what you need is a prism or a spectrometer which uses a prism. So why do elements not emit continuous spectra, and why does each element emit a particular lines on the line spectra? Well, this is going to lie in that Bohr theory. Bohr found that electrons move in particular orbits within the atom, meaning electrons have particular places or levels. The fact that we can draw it in a specific orbital means that's where it should stay, is in that orbital. Electrons have certain allowed energy values. Electrons have certain allowed energy values. The closer the electron is to the nucleus, the lower the energy. Which means if I add energy to an electron, the electron's going to be excited, it gains energy, and it will move to a higher energy level further away from the nucleus. So we add electricity, or we add fire, or we add energy in some way to make the electron jump. Same thing, if I added electricity or if I added fire to your feet, you jump as well. So you add energy and they jump. However, they don't have enough energy to stay in the air, just like you wouldn't have enough energy to stay in the air. So instead of being able to stay at the higher energy level, the electrons give off light, they emit energy, and they move closer to the nucleus. They go back down to what we call the ground state. So if I make you jump, I add energy to you, you jump, you're going to fall back down to the ground state. The electrons do the same thing. You add energy, they jump up to a higher energy level, but then they fall back down to the ground state. What's different is when an electron does it, an electron emits a photon of light when it falls back down. When it releases that energy, it releases light. So based off of where that electron jumps, if it went from the second orbital all the way out to the sixth orbital, when it falls back down, the color it emits would be purple. It would emit blue if it fell this far, green, or red, depending on where it falls from. So if I add a whole bunch of energy, and my electrons jump to different orbitals, when those electrons fall back down, they emit a color. Now if I continually add energy, continually add electrons or fire, or electricity or fire, these electrons will continually jump. And they continually jump, continually let off that color, and so the red is continually let off as long as it's being added energy. Now when electrons are excited, they absorb energy and move to the higher energy level. So that would be your yellow arrow. All right, we gained energy, we jump to a higher energy level. When they move to a lower energy level, we call it the ground state. When it moves back, it's the ground state. We call the measurable amount of light energy released a photon. The measurable amount of light energy released is a photon. Violet light is produced when electrons move from 6 to 2. Blue is when it moves from 5 to 2. Green moves from 4 to 2. Red, 3 to 2. This series of lines, which is visible in the hydrogen line spectrum, is called the Balmer series. So the visible line spectrum is called the Balmer series. The energies of these emissions just happen to be in the visible range we can see. There are other transitions which occur, but since they are not in the visible range we see, we cannot see them with our eyes. Some have wavelengths less than 400 nanometers, and some have wavelengths greater than 750. Remember, we only see from 400 to 750. So that Roy G. Biv, those colors that we can see, only fall in that range. So if they do release energy in other ranges, we can see them with their computer systems or with certain photography systems, but your eyes can't see them. You're going to come back and answer these questions just off of the notes above. Go on to the next page. So the emission spectra for each element, or the atomic spectrum, can be used as a fingerprint for that element. Because it is independent on which element it is, then the emission spectra can be a sign or a fingerprint for that element. Only one element will have that specific emission spectra. So we can analyze the light emitted by high temperature gaseous elements to see their individual spectra. So if you were to look at just a regular light bulb and you put that through a prism, you see the entire spectrum, Roy G. Biv. Because this isn't just one element, there's several elements happening here, and we see all the colors. But if we look at the spectra of just one element, so if we look at just hydrogen, or if we look at just mercury, which is the example I have in class, we will see only its spectra. So for hydrogen, once again, it has this very distinctive fingerprint. Now, a way to think of this is with a turtle analogy. So if I have a turtle sitting at the top of a ramp, he can be any height above the ground and therefore has any potential energy. He can move a half step forward or several yards forward. At any point on the ramp, his energy is completely changing. But if he's on a staircase, he can only go one step up, one step down. So it's in this very set amount of energy. Anytime you move up a step, you need to absorb energy. So energy is required to move up. So that would be absorption. Energy is released to move down, emission. And because he's on a staircase, only discrete amounts of energy are absorbed or released. It is quantized. Because there is a step, a very set area where you can go step, then your energy is quantized. So the energy diagram for the atomic hydrogen, the bottom step would be the ground state, and the higher steps are the excited states. If an electron has jumped to a higher state, it's just like jumping to a higher step. It's now in an excited state. It'll fall back down to the ground state. The quantum level occupied by an electron in an atom depends on the energy of the electron. Changes in quantum level are related to the absorption or emission of energy. The figure below represents the 4 lowest energy levels of an atom. The 6 lettered arrows represent changes in energy of an electron. So I'll do the first question with you. Which 3 of the lettered energy changes involve absorption by the atom? So there's 3 letters here that show absorption. If my arrow is going down, then the electron is falling. In order for an electron to fall, it must have released energy. So down arrows are releasing energy, up arrows are absorbing energy. Therefore, the 3 that show absorption are B, D, and F. Once you finish these 2 pages, make sure you look back through all this information here. It summarizes the entire part of going through emission spectrum. So make sure you read through all of this. This is very crucial for your understanding of this section of knowledge and for preparing you for your lab tomorrow. So get out your pre-lab that's at your table. All right, we have a flame test. A flame test is going to let you identify elements using that emission spectra we just talked about, the different colors emitted from the different elements. So we're going to add energy to these elements by putting them in the flame. They'll release a color. This is the chemistry behind fireworks. You will see all the colors that they use whenever they make fireworks. So make sure you go through and read all of this information. It's very crucial for you to be able to answer your lab questions. Whenever you do your calculations, make sure you use your wavelengths from the table inside your workbook. If you notice, the wavelengths on this table are in nanometers, which means you would need to convert from nanometers to meters for all of your calculations. So it'd be easier just to use the one from your workbook in all of your calculations. You will be writing your first formal lab report. This will be for a major grade. For your formal lab report, you need a title, and you will have each one of these sections, and you need to underline the section heading. So at the top of your page, write flame test lab. On the first line, write your name. On the second line, write the word lab and then partners, lab partners, and then colon. Underline that, and you will fill that in tomorrow when you do the lab. So at the top you should have flame test lab. The first line should have your name. The second line should say lab partners, be underlined and have a colon. Now skip a line, and you will copy the purpose. Then you'll skip another line, copy the materials. Skip another line, copy the safety. Skip another line and copy all of the procedures. Skip one more line and do your pre-lab questions. Now, if you look at the instructions for your pre-lab questions, it says you may require further research to answer, and you need to copy the questions or answer in complete sentences. If you do not write down the question, then I need to be able to identify what the question is from your answer. You have 5 pre-lab questions. Number 4 will help you set up for doing the calculations you'll need for this lab. If you notice in the lab, you'll be taking wavelengths and calculating energy. So make sure you know how to do the calculations from wavelength to energy. Number 4 will be a good practice for you. By the time you come to class tomorrow, you need to have completed through your pre-lab questions, and you will turn that in. In class tomorrow, as a lab group, you will fill out your data table, work on your post-lab questions, and your conclusion. That will be due on Thursday. The 2 parts, your pre-lab and your post-lab together, will be worth a major grade.